So welcome to my talk on .NET Core Data Security, Hope is Not a Strategy. My name's Stephen Haunts. I'm an author for Pluralsight. I've been with them for about 6 years now. I've done 21 courses with them. A freelance trainer and also a Microsoft MVP, which means you get a nice little blue badge. It's all about the blue badge. Okay, so the reason why I do this talk, and I've done various different versions of it, and this one's tailored more towards .NET Core, is because as developers, it's kind of our responsibility, I believe, to try and protect the information assets of our company by making sure that we encrypt their information and do key management securely. A lot of companies tend to have this kind of attitude, or certainly ones I've worked with back in the UK, where if we just cross our fingers, we'll hope that no one tries to steal any of our data from our databases, and then end up in have I been pwned, which is what nobody wants. So generally, we tend to get companies using hope as a strategy or a security strategy. I've worked for many companies across many different market verticals, financial services, healthcare, things like that. And there has been kind of a blasé approach in some instances. And this is kind of like a typical manual that you might get when you're working with a project management team. Okay, that one didn't get a laugh. We're on to a bad start. Okay, so what this talk isn't about, so this talk isn't about maths. It's not about how things like AES work under the covers. As interesting as it is, as developers, you don't really need to know that unless you particularly want to peer under the covers. It's also not about breaking codes, cryptanalysis, or any of that sort of cool stuff. What it is about people like you and me who are on the front lines in our companies building software solutions. Pretty much every developer I meet always has the same story, that there's never enough time to deliver what they need to do, and the company wants everything now. So this talk is aimed at people that are working on software systems. They want to know about how to do cryptography and other things in .NET. So this is kind of like a little intro to kind of what you can do. So typically, a lot of this stuff originated from the .NET framework, or the more traditional .NET framework. Typically, it would run server-side or in client code. But when Microsoft started the .NET Core journey, certainly around 1.0 and version 1.1, the cryptography support in that version of .NET Core was severely lacking. You had a few hashing functions, and that was pretty much about it. So .NET Core really became a serious contender from .NET Core 2.0 and .NET Standard 2.0, which was great. We started to get some feature parity with the .NET framework. And the good thing is now, now we're in the realm of .NET Core 3 and above, we actually get a few more additions that we've been waiting for in .NET for a long time, which we're going to talk about today. So whilst this is a very Microsoft-focused talk in that we're looking at some of the APIs that are available to us, in essence, the principles of what we're discussing are kind of universal. So whether you work in Microsoft.NET, PHP, Java, Python, Node, it doesn't really matter. The principles are kind of the same. Just we're looking at a Microsoft API. So what we're going to cover, and cover quickly, is anyone here who was in my workshop? No, that's good, because they're basically going to get the same information again. So we're going to look at random numbers, we're going to look at hashing and HMACS, HashMessage authentication codes. We're going to take a little look at secure password storage, symmetric encryption with AES, and the new AES-GCM mode, which has just been introduced into .NET. We'll look a little bit about asymmetric encryption and RSA, although I'm sure everyone was in the keynote this morning and is now worried about RSA. And we'll look at digital signatures, which also suffer the same quantum-related problems, but we'll save that problem for another day. And then we'll look at some examples about how typically some of these things might be combined together. So how things like end-to-end encryption work or TLS protocols work. So we'll look at how you can mix some of these things together. So what is cryptography? So it's generally about protecting information. Typically we think of encryption when we're doing that, which involves encryption keys. The result of an encrypted message is often called ciphertext. And the art of trying to break cryptography is cryptanalysis. But really there's a lot more to cryptography than just encryption. So there's kind of 4 core pillar areas that we talk about with cryptography. So we have confidentiality, encryption, making something confidential. We have integrity, so making sure that if I send a piece of data to someone, that it hasn't been tampered with or corrupted in transit. We have authentication, which is similar to integrity, but it's about, do you have permission to check the integrity of this file or piece of data. And then we have non-repudiation, which is about being able to prove you as the originator of a message. So cryptography is used everywhere, and you literally cannot get out of bed without cryptography being involved in your life somehow, even though generally it's quite transparent. So online shopping, if you go onto Amazon or any other website, just using your browser, you have your browser and servers, negotiating keys between each other and communicating securely. Taking money out of an ATM, there's a cryptographic handshake that goes on when you put your PIN code in. Mobile phones, for better or worse, are pretty well encrypted these days, especially iPhones. But then also we've got some more, non-security related things like Bitcoin and the other 4 million coins that are out there in the world today. And also electronic voting systems as well. I don't know if anyone went to the talk on electronic voting earlier, or voting. It was quite interesting. Okay, so we'll start off with random numbers. So random numbers are kind of important to cryptography. It's what we use for generating a lot of encryption keys or salts on passwords. So having the ability to generate good random numbers is quite important to us. Now, traditionally when you talk about random numbers, people think about system.random. And whilst it's good for generating lottery numbers or dice rolls or anything like that, it's not really robust enough to use for cryptography, because if you pass the same seeds into system.random, you'll get the same set of numbers out. So it's deterministic, which is not good. So instead, you can use something like RNG Crypto Service Provider, which lives in system.security.cryptography, along with everything else that we're talking about today. It's very easy to use. So if we look here, we have a method. We pass in a length. That length is going to be the length of a byte array that we want to initialize. So if you're using a 256-bit AES key, for example, that would be 32 that you pass into there. You instance the RNG Crypto Service Provider, initialize an array to the desired length, call get bytes, and then that array is populated with lots of random data, which is fantastic. It's returned as a byte array. So hashing is the next set of primitives that we're looking at. And I guess is probably the one which most people are familiar with and tends to get used the most. And hashing, a good way of thinking of it is it's kind of like an electronic fingerprint for a piece of data. So if you have some data, be it a PDF document or a string, credit card number, whatever, pass it into a hashing function and you get a hashing code out the other end. If you modify that data just slightly and rerun the hash code, you get a completely different hash code out the end of it. So there's four core properties for hashing that we try to adopt. So first of all, it should be easy to compute. Piece of data, pass it through a function, get a result. It's going to be easy. It should be infeasible to generate a specific hash. So you shouldn't be able to start with a hash code and think, what piece of data do I need to generate this hash? You shouldn't be able to pre-guess what that data is going to be. It should be infeasible to modify a message without changing the hash. As already discussed, if you change just one bit in your original data, you expect the entire hash to change, not just a little bit of it. And it should be infeasible to find two identical hashes. So if you have two different pieces of data, and you run them through a hash algorithm, you shouldn't get the same hash code out the back of it. That's called a hash collision. And somehow algorithms are susceptible to hash collisions. I think SHA-1 has been recently as well. Another good way of sort of framing a mental model around hashing is it's kind of like one-way encryption in a way. So you have a piece of data, you generate the hash code, but you can't go back from the hash code to the original piece of data. It's a one-way operation. Whereas encryption typically is a two-way operation. Have some data, encrypt it with a key, decrypt it with the same key, you get your data back. Now, MD5 is quite an old hashing algorithm. It produces a 16-byte hash value, invented by Ron Rivest of RSA fame. It came out in 1991, but it was discovered to have a hash collision resistance vulnerability in 1996, which means it's not what you'd want to use in a brand new system, but it's still worth talking about and knowing about it, because if you're, like I was at a bank, integrating with some older systems that sent you MD5 hash codes back for some data, you still had to know how to generate them in .NET. So for legacy supports, it's still relevant. Then you've got the secure hash family. So you've got SHA-1 and SHA-2, which are available in .NET Core. So SHA-1 gives you a 160-bit hash function, which is 20 bytes. And then you've got SHA-2, which gives you 256 bits or 512 bits. so 32 and 64 bytes of our hash data. There is a new one called SHA-3, which was designed, well, the original SHA algorithms were designed as part of a competition which were run by the NSA. Obviously that makes people a little nervous. So SHA-3 was a competition to come up with a new algorithm that didn't have NSA involvement. That is now adopted as a standard, but Microsoft hasn't implemented it yet. There are open source versions of it you can get, but obviously it's up to you whether you trust those or not. Hashing, very easy to do in .NET. So if we look at SHA-256, for example, got a sample method here. We pass in a byte array of our data that we want to hash, because typically everything works with byte arrays in cryptography. You just call the static method create on the SHA-256 object, then you call compute hash, pass your data in, then you get a hash code back. So very, very powerful property that hashing gives you, but it's actually very easy to use, which is fantastic. That's what we want. So building on top of that, we have what's called authenticated hashing. And this is pretty much the same as normal hashing. Have some data, run it through the function, get a hash code back. But in this case, you also provide a key as well, like an encryption key, so a 32-byte key. So what this means is if I generate a hash code for a piece of data and I send it to one of you, if you want to generate that exact same hash code, you have to be in possession of that key. If you have a different key, then the hash codes won't match. So you can kind of think of that key as a bit like a really long password, in a way. So HashMessage authentication codes, they verify integrity and authentication. You can use HMACS based on MD5 and the SHA family of hashes in .NET. Strength is based on the key length, so obviously the longer the key, the more secure that's going to be. And the most common attack against it is a brute force against that key. So that's where you just keep on trying, millions of combinations until you get the right key. Again, very simple to use, just a few lines of code in .NET Core. So you have a HMAC SHA-256 object, pass the key into the constructor, then you call compute hash on your desired piece of data, and you get your hash code back out the other end. It's the same if you're doing a HMAC SHA-512 or HMAC MD5. It's the same interface. So a little detour into passwords. So unfortunately, passwords are here to stay. I know we're trying to encourage our users to use things like two-factor authentication and better authentication methods, but a lot of users still prefer passwords because it's easier for them to remember. So how we store those passwords is very important. But when you get data breaches, where you have people's usernames and password hashes in there, typically you're going to get things like a brute force attack against that password, which is where you use a tool like Hashcat to repeatedly, just try billions of different combinations until they get the same hash for a password. Or you can do what's called a dictionary or rainbow table attack, which is a massive pre-computed dictionary of passwords. So all they have to do is just pass the hash into this dictionary and it will just tell them what the password is. And these dictionaries are gigabytes in size and you can just download them freely off the internet. Using a tool like Hashcat, which uses whatever GPU is installed on your system, obviously means it's very, very fast. A good demo I've done for some of my more corporate customers before is you use a tool like this, which is crackstation.net. You can paste a SHA-256 hash in there, you just type in the captcha code, hit crack hash, and it tells you what the password is. So it's kind of a good little demo that you can do to scare executives. The next better way of doing it, and this is probably still one of the more common ways in which companies store passwords, is you have a password and then you append what's called a salt onto the end of it. So a salt is just a random piece of data that you generate, like a large random number. Append those together, call the hashing function, then you store the hash and you store the salt. So the idea is it's supposed to make it harder to do a brute force attack. Although if someone manages to steal all the salts and can tie them up with the passwords, then obviously that becomes a moot point. Anyone use that technique in their companies? Yeah, so it's still quite common. So really what we want to try and do is we want to try and make sure that trying to crack these is more difficult. And with Moore's law and processor speeds and GPU speeds increasing constantly, they can detect 2, 3, 4, 5 billion combinations per second on a powerful GPU. So what we want to do is to we want to deliberately slow down the hashing process. which is where we'll look at something called a password-based key derivation function, which if you're not familiar with it, it sounds quite frightening, but it's actually quite simple. So a password-based key derivation function, or PBKDF2, as it's commonly known, is very similar to a salted hash. So you have your password, you pass in a salt, and you pass in a number of iterations. What that number of iterations is going to do is it's going to repeatedly hash the password before it returns the hash to you. So if you put a number in there like, 352,427, it's going to do, over 300,000 repeated iterations before it gives you that hash back. So that means if anyone's using Hashcat to try and crack your passwords, instead of doing billions of combinations per second, you might be able to reduce them down to 1,000 or 100, or depending on what value you set. You might notice on some websites when you put your username and password in, it feels like you're waiting, 3 to 5 seconds before anything happens, probably because they're doing one of these behind the scenes, or an equivalent like bcrypt, which is kind of conceptually similar process. Yep.
Where do you store the salt? Because I guess you store the hash to password somewhere, but where do you?
Well, you need to store it somewhere in your database because you need to present the same salts when you hash your password. Yeah. So a PBKDF2 actually has a proper standards name. It's an RFC 2898. So whoever implemented this in .NET decided to call it RFC 2898 derived bytes. Not really obvious what it does unless you're intimately familiar with RFC numbers. I guess, to some people it makes complete sense. But, if you saw that in the documentation, you'd probably just skip over it because it doesn't make sense. Which is a shame because it is incredibly easy to use. You just instantiate the class, pass in the data you want to, or pass in the password as a byte array, pass in your salt, give it a number of iterations, and then you call get bytes. The reason you return 20 in this case is because this implementation uses SHA-1 internally, which gives you a 160-bit hash, which is 20 bytes. So the number of iterations you pass in obviously means it's going to take more time. When I calculated that table, I was using a much older laptop. I tested it yesterday with, on this machine here with several million as the iteration count, and it still took less than a second. So you need to think about what's an acceptable level of delay for your business. That's kind of a business decision. Obviously, the higher that number, the more secure that password's going to be. So I know Troy's mentioned this in his talks, but this is a good example. So has anyone heard of Ashley-Madison or the Ashley-Madison data breach? So this website can really be described as kind of like a dating website, I guess, that encourages people to have affairs. It's pretty shady what it does. I don't particularly like them, so when they got hacked, I was like, yes. But there's an interesting story behind it, and this must have been an inside job as well, because as well as all the passwords being stolen, all the usernames, etc., all of the source code was extracted as well, which makes it kind of feel like it was an inside job. So with their passwords, they used something called bcrypt to hash their passwords. It's similar to what we've just looked at in .NET. It's just an alternative implementation. So they were using bcrypt for their passwords, which is great. It's quite good password security. But when they looked through the source code, they found that some enterprising software developer tried to optimize the process slightly so that you can log in faster. So after your first login, it would then store an MD5 hash of the password, so you can speed up the login process next time. Brilliant. Once they found that out, they obviously managed to go and easily reverse engineer all of the passwords, because MD5 hashes are incredibly easy to crack these days. If you're interested in that story in further detail, Ars Technica did a fantastic news piece on kind of what happened and what the ramifications were. Another reason I like to include this in talks, obviously it's a horrible website, and when all this data leaks, it had quite a big impact on people's lives. So obviously if you've been caught having an affair and your username's in there, that's quite embarrassing. So people, it broke up families. The most severe cases, a few people actually committed suicide over it. So it just goes to show that what we do as software engineers can actually have quite a big human impact. Anyway, on that low note, let's move on. So symmetric encryption. Sorry to be a downer. So symmetric encryption. This is where we start getting into some of the fun stuff. This is where you encrypt data with a key, decrypt it with the same key. I'm sure everyone knows that. You know, we're at a security conference. But the problem with symmetric encryption is sharing keys is hard. It's very hard. I mean, if I want to encrypt some data and send it to one of you, how do I get that key to you? I'm not going to stick it on a text file on D drive, although I've seen that happen. I'm not going to email it to you. Maybe I could physically meet you and hand you a USB key. That might be a good way of doing it. But getting the keys between people is very, very hard. So that's one of the downsides of symmetric encryption. Again, going back to our mental model where we talked about hashing. So hashing was a one-way operation. Encryption is two-way. So the way encryption algorithms work is they take a load of data, they split it down into blocks. The blocks at the end might be padded in some way if they don't quite fill up the block. And then you have lots of different repeated operations which happen on these blocks where they get, different processes done to them, and they get XORed together, and then eventually out the other end you're going to get some encrypted data. So for computers, this is very, very fast. This is what computers are good at. It's just good algorithmic support. Now we have, prior to .NET Core, we have things like AES Crypto Service Provider, DES Crypto Service Provider, and Triple DES Crypto Service Provider are kind of free symmetric algorithms available to us. They all derive from a symmetric algorithm-based class, which means they're all pretty much identical in how you use them, which is good. DES and Triple DES, again, you're not going to use those in a brand new system, but if you are in a larger, older company, chances are you might have to integrate with some older legacy systems. So I worked for an online bank. It was one of the first online banks in the UK, but our back-end banking platform was like a Unix-based AES-400 mainframe system. And all of our data was encrypted with Triple DES. So obviously we had to deal with some of that data. But generally, if you're going to use a system these days, you're going to use AES. So AES is a NIST standard from 2001. So based on the Rijndael cipher by two Belgian mathematicians, Joan Damon and Vincent Riemann. And the way this works is to pass into this system, you have your plain text, that's the data you want to encrypt. You have different key strengths, so 128, 192, or 256-bit keys. You're generally going to go for the higher key length, 256 bits. And you're also passing something called an initialization vector, which is a 16-byte random number, which is used to basically jumpstart the first block of the encryption. The initialization vector, you do need to store it with your encrypted data, because you have to pass the same IV back in when you decrypt your data. But it's not a secret key, it's not classed as a secret. Now in .NET and .NET Core, there's two versions of AES, or the older version of AES. It's AES Managed or AES Crypto Service Provider. The difference is AES Managed is written in .NET, it's a native .NET implementation, but it's not FIPS certified. Whereas AES Crypto Service Provider uses the underlying Windows cryptography platform, and it is FIPS 197-2 certified. What that means is it's been independently tested, which means it will be compatible with other implementations that also have the certification. So if you've got some data that was encrypted with Java's implementation, if their one's FIPS certified, it means you're going to be able to download the same information. So generally, you'd tend to use this. Reasonably straightforward to use. So it uses streams, uses a memory stream and a crypto stream. So we pass in our data, the key and the IV, instantiate the AES Crypto Service Provider, initialize our streams, pass the data in. Got this thing here, AES Create Encryptor, which you have to call. Call write, call flush block, turn it into an array, return it, and that's your encrypted data. Decryption is identical. The only difference is instead of create encryptor, we're passing in create decryptor. So it's relatively straightforward. And this is what we've had available to us in .NET and .NET Core for a long time. Well, not so much a long time for .NET Core, but traditional .NET, this is kind of what we've had to play with. Now in .NET Core, we get something called AES-GCM mode, or Galois counter mode. And there's another version called CCM, but GCM is the most useful version to us. And this is good. GCM mode in AES has been around a while, but it's only just come to .NET, which is good. Now, traditionally, when you use normal AES, like the one we just looked at, a traditional use case would be that you encrypt some data, and then you might produce a HashMAC of that data afterwards, which you then store with the data. So here's some encrypted data. I've now got an authenticated hash of the data, so we can tell if it's been modified at a later date. What GCM mode does is it does that hashing process as part of the encryption process. So instead of doing an encrypt and then hash, we're basically getting the whole thing done in one go. And GCM mode has been designed to be highly parallel and very, very fast and efficient. There's even internal instructions on modern chips. Now, instead of passing in a 16-byte initialization vector, they've now called it a nonce, number once. And instead of being 16 bytes, it's 12 bytes for GCM mode. Also, you pass in your key, so 32-byte, 256-bit key. And you can also pass in what's called associated data. So this is effectively metadata that you can pass in along with your data that you want to encrypt. So a good example of that might be if you're encrypting personal information for a customer, so name, address, phone number, date of birth, etc. The associated data you pass in might be the database key ID, which isn't necessarily relevant to that record on its own, but you might just pass it in as a bit of additional metadata. You don't have to pass it in, you can just pass null if you don't want to do that. What we also get out, which I've actually left the arrow off of the diagram, that's a bit silly. There's another thing we get out as well as the ciphertext, it's called a tag. Now that tag is effectively a HMAC of the encrypted data. So to use it, it's very straightforward. So we have a method here, which I've written. So we pass in our data to encrypt, we pass in our key, 32 bytes, pass in the nonce, 12-byte random number. We pass in our associated data if we want to. We initialize an empty tag. We create an array for our ciphertext. We instantiate the AES-GCM class, passing the key into the constructor. Then you just call encrypt. And then from that, I'm returning a tuple, or tuple, or tuple, depending on how you want to pronounce it, of the ciphertext and the tag. Now, when you come to decrypt the data, you pass in your ciphertext. Obviously, that's what you want to decrypt. You pass in your key. You pass in the nonce. You pass it the same tag that was returned previously. And you pass it the same associated data, if there was any. Now, what it will do is when you pass that tag in, it's going to check the integrity of that data as it's decrypting it. If there's an issue with it, it's going to abort and throw an exception. So whereas before we said you do an AES encryption, then a HashMac, and then what you might do is you might do a HashMac check and then a decryption. This is doing it all as part of the same process. Okay, so asymmetric encryption, this is discussed this morning, so everyone's probably familiar with it. So it's based on the idea of having a key pair, a public key and a private key. These keys are based on prime numbers. So what it will mean is if I want to send some data, encrypted data to one of you, what I do is I request your public key, which you send me, because it's public, anyone can know that. I encrypt the data with your public key, I send you that data, and then you decrypt it with your private key, because it's only known to you. So RSA was developed by RSA Data Security Incorporated by Rives, Schemmer, and Edelman. And it's based on the fact that there's no way to factor very large prime numbers, caveat, until quantum computers come along. A minimum recommended key length these days is 2048 bits. But whenever I've used it, we've gone straight to 4096 bits, which is a nice, strong key at the moment. So RSA is a mathematical encryption scheme as opposed to being algorithmic like AES. AES is incredibly fast and efficient, but sharing keys is hard. Asymmetric encryption, the key sharing problem is better because you've got this split key concept, but it's incredibly slow to encrypt data with it. There's also a limit as well in that you can only encrypt data up to the size of the key, including your padding. So you can't just have a huge piece of data and then encrypt it with RSA because it won't work. So if I was to say, so the whole idea around prime numbers, if I was to say to you, what is 23 times 17? Obviously, I'm not going to make anyone do it, I'll just put the answer on the screen. But, that's quite an easy sum to work out. I nearly had a heart attack this morning because I thought she was going to ask me that maths question, but I managed to dodge that one. She took the guy next to me. So the answer is 391. very easy to work out. But if I was to say to you, and if anyone can work it out, please let me know, what are the two prime numbers that make 5,963? That's quite hard to work out. Anyone want to have a quick guess? No, okay. So 67 and 89. So if we equate this back to our mental model around public and private keys, the public key is the result of those primes, 5,963, and the private key is those two factored prime numbers. Now, a real RSA key has more components to it, but that's kind of like the fundamental principle. But an RSA key is going to be a lot bigger than the number 5,963. It's going to be from here, probably stretching into the centre of Oslo. It's a really, really long number. So trying to break that number down to its constituent prime numbers is incredibly hard, and that's what computers struggle with at the moment. I'm saying at the moment, I'm being very cautious. So using RSA in .NET is incredibly simple, which is great. So first of all, you want to generate some new keys. I didn't design these APIs. Some of the API designing this is a bit questionable. But so I've got a method here called assign new key. You instantiate RSA crypto service provider, tell it what strength key you want. Then you call export parameters by passing in false to get your public key, and you pass in true to get your public key. So that that puts the two keys in those private properties at the top there. Encrypting data, again, only a few lines of code. So you instantiate RSA crypto service provider, you import your public key, because you always encrypt with a public key. We call encrypt, giving it our byte array of our data, and that's going to return our encrypted data to us. To decrypt it, again, we instantiate RSA crypto service provider, we import our private key, or the recipient's private key, or they import their key, I should say. You call decrypt, then that gives you your decrypted data back. So that's RSA, incredibly simple to use in .NET. The final primitive I want to look at, before we sort of look at how typically some of these things are used together, is digital signatures. So a digital signature has three kind of properties, or three methods to it. There's the key generation. You have a signing algorithm for signing some data, and you have what's called a signature verifier. Now, the reason we sign data is because it's a good way of proving that some data originated from us, or from you. So if you think about what we said with RSA, if I want to send some data to you, I request your public key, I encrypt the data, then you decrypt it with your private key. The signing process is kind of flipped. It uses RSA, in this case, under the covers, or the one we're going to look at. But instead, me as the originator, I sign the data with my private key. Only I have that private key. So when I send you the data and you want to verify it came from me, you verify it with my public key. If the verification process comes back and says true, you know that that data could have only come from me, or a criminal that's stolen my private key. Now, because it's based on RSA, as you said, there's limits to the amount of data that you can process in one go. So typically what you do is you create a SHA-256 hash, or HMAC of that data that you want to sign, and then you sign the hash, which is a much smaller piece of data. Okay, so again, very easy to use. So the key generation process is exactly the same slide as what we saw before for RSA. To perform a digital signature, or to sign it, we have to use this class here called RSA PKCS1 signature formatter, which is a brilliant name. So we instantiate the RSA crypto service provider, we import our private key, because as the person doing the signing, I'm going to use my private key. We instantiate RSA PKCS1 signature formatter. We tell it what hashing algorithm we're going to use by passing in a magic string that says SHA-256. And then we call create signature, passing in the hash of our data. And that will give us a byte array back that contains our digital signature. So we send some data to a recipient. So we send them the hash of the data that we wanted to sign. We send them the signature. And they come along and they request my public key, or maybe they've already got a copy of it. They import the public key. They call RSA, or they instantiate RSA PKCS1 signature deformatter. Again, tell it that they're using SHA-256. And then they call verify signature, passing in a hash of the data and that signature, and it will return either true or false. Yes, it verifies. No, it doesn't. The digital signatures, they're very useful. Has anyone used services like DocuSign to sign contracts or some of the equivalents? So taking DocuSign as an example, if you're wanting to sign a contract with someone for a piece of work or to buy a house, they upload the contract into DocuSign, you read it, you tell it you want to sign it, and it puts a nice little pretty graphic of a signature on there. Behind the scenes, it creates a digital signature, like what we've done here, and that gets stored in a database. Then the next person comes along, the originator of the document, if you've signed it, they then countersign it, and that creates another digital signature. So what this also means is that, if it was, say, for a piece of work, and you agreed that they're going to pay you 10,000 euros for this piece of work, if you then come along and say, no, actually, I want 15,000, they're going to go, well, no, we've got mathematical proof that you signed this document with your private key, and we countersigned it, so we have proof that that document says 10,000, not 15,000. So that's kind of how services like DocuSign implement digital signatures. And it's handy because you can use digital signatures as proof in court. Okay, so we talked about the 4 pillars earlier. So confidentiality, well, we looked at AES and RSA for that. Integrity, we looked at SHA-256. Authentication, we looked at HashMAC SHA-256. And non-repudiation, we looked at digital signatures. So kind of some example primitives in .NET that we can use to satisfy each of those 4 pillars. So what I want to look at now, I've only got 20 minutes, so what I want to look at now is how some of these things might get used together, because it's like a box of tools, and you have tools and you combine them together to produce other tools. And this will give you kind of a good idea of how things like end-to-end messaging or maybe TLS, things like that work, which is good. So let's start off with the first example. So we talked about how the fact that RSA has limits on the amount of data that you can encrypt in one go, so that's a limitation. But we also mentioned that AES is incredibly fast and efficient, but key sharing is hard. So what we can do is we can use 2 of those together to give us a way to have fast encryption with good key management. So if we work this through as an example, so if we generate an AES key, which is 32 bytes, as we demonstrated earlier, we encrypt our data with AES, nice and fast. Then we take our recipient's public key and we encrypt that key that we've just generated. Then we send our AES encrypted data and that encrypted AES key over to our recipients. First of all, they use their private key to decrypt that session key. Once they've done that, they've then got the raw AES key. So we've managed to get that key to the other person securely. Once they've decrypted that key, they can then go and decrypt the AES data we sent them and read the message. Yeah? So if you think about something like TLS as an example, what happens when you create a connection to a server? You've got your 2 parties, they swap their public keys, they generate a session key, potentially with AES, they use RSA to swap that key between each other, and then they've got a channel that they can send encrypted data backwards and forwards. Fundamentally, it's a similar principle. So if we think of that as a packet of data that we're going to send to someone, so we have our RSA encrypted session key, we've got our AES encrypted data, and we also have the AES initialization vector. So I should have mentioned that in the previous diagram. But let's walk it through as an example. So we've got Alice and Bob, and they're going to have a 2-way conversation with each other. So let's work it through. So Alice generates a key. She generates an initialization vector. So the IV is 16 bytes. This AES key is 32 bytes. She encrypts her message with AES. Then uses Bob's public key to encrypt that AES key. Sends it over to Bob, where he can then start the process of reading it. So what he does is he uses his private key to recover or decrypt that AES key. He then uses that decrypted AES key and his initialization vector, which he can then use with AES to decrypt the message. So the message was, meet me at noon below the clock tower, wear a red rose in your button. Try to make it a bit more James Bond. Great, so now Bob wants to send a message back to Alice to confirm his meeting with her. So he generates a new session key in this case. He generates a new initialization vector. He encrypts his reply using those pieces of data. He then uses Alice's public key to encrypt his new AES key, sends a message to Alice, and she can then start the process of reading it. So she uses her private key to recover that key. Once she's got that key, she uses AES to decrypt the message. And she's like, I will meet you, I'll be wearing a blue hat and red boots. She's the height of fashion. Yeah, so when you send the message to the recipient, they have to have the same IV, so you send the IV to them. Oh, because they sent the new IV back. So if you think of it as a packet of information that's being sent between the people, where's the slide? So that's what's being sent, the RSA encrypted session key, the initialization vector, and the encrypted data. Okay. Where are we? Lost my slide now. Okay. So the next thing you might want to do, so if we're using the older version of AES in .NET, the non-GCM version, this is what we might want to do next. So exactly the same process. Generate the session key, generate an IV, encrypt the data with AES, encrypt the session key with the public key. Now what we're going to do is we're going to get our ciphertext, we're going to get the IV, we're going to combine them together, and then we're going to create a HashMAC using that AES key as the key. And then we're going to send that HashMAC along with the rest of the data that we send across. The reason for that is, on the other side, Bob has got to recover the AES key. Once he's recovered that key, or decrypted the key, he then has the ability to calculate the same HashMAC that was sent, so he can compare them. If they're the same, he knows no one's tampered with the data, and then he can go and decrypt the data. So this gives him the concept of integrity and authentication, because we're using a HashMAC. So not only have we solved the problem of how do we get a symmetric key between two parties, we've also guaranteed that you have to decrypt that key first to calculate the hash. So obviously the recipient needs their private key or the correct private key. And we can also tell whether that message has been tampered with or corrupted in transit. So if we look at the packet of data that we'd send, so obviously we're sending the RSA encrypted session key, the initialization vector, the AES encrypted data, and also our hash of the encrypted data in the IV. The reason we include the IV in that HashMAC is because if someone messes around with the IV, we want to be able to tell if it's changed. So by including it in the HashMAC, we can tell that. So if you was using GCM mode, it's slightly different because in Galois counter mode in AES, we don't need to calculate that HashMAC afterwards. It happens internally inside the algorithm for us, which is good. So actually our diagram, if we was using GCM mode, looks very much like the first diagram. We encrypt some data with an AES key, we encrypt the AES key, and we send it to the recipient. But because AES uses a nonce instead of an IV, we store that nonce in the packet. And because GCM mode returns us a tag, which is effectively a HMAC, we also store that tag and we send it to the recipient. So the process is, it's a little bit more simple, less code to write, which is nice. Okay, so we've managed to swap our keys. We've managed to add integrity and authentication into the process. So now let's add the final pillar and see what that looks like, and we'll do we'll do non-repudiation. Okay, so as an example again, exactly the same. Generate an AES key and an IV, encrypt our data with those pieces of information, use the recipient's public key to encrypt our AES key. We need to create a HashMAC of the ciphertext, the nonce, and the tag. And I'll come on to why in a moment. But we need to, even if we're using GCM mode, we still have to create a HashMAC in this case. And we then use that HashMAC that we pass into our digital signature algorithm to create a digital signature. Now you might be thinking, if the tag is a HMAC, why do we need to generate another HMAC? That's because that tag is a different format than what the digital signature algorithm is expecting. So if you pass that tag into it and tell it that you're doing a SHA-256 hash, it just won't know what to do because it's a different format. So that means in this case we have to do a HashMAC anyway. So that means our packet of information looks like this. We've got the session key, the initialization vector, or nonce, The encrypted data, we have our HashMAC, and we have the digital signature. So the benefit that this gives us then, so again, we've got the ability to securely transfer a symmetric key between two parties. So we've solved that problem. Obviously, we get confidentiality because we're encrypting our data, and we've got the keys safely swapped between people. We've got integrity and authentication because we've got this HashMAC or tag from the encrypted data, so that's good. What the non-repudiation gives you is proof that it was you that sent that piece of data. Because you create a digital signature with your private key, when Bob comes to verify the signature on his end, he has to use the sender's public key. If it returns true when he verifies, he knows it was Alice that sent that message. Does that make sense? So it means you can verify the authenticity of that message, the originator, which is quite cool. So when you hear in the press, you hear people talking about how evil end-to-end communications are. Effectively, what's going on behind the scenes is something very similar to this. So if you download the spec for the Signal protocol, obviously the Signal protocol is more complex than this, but fundamentally it's doing something very similar to this. It's using an asymmetric system for negotiating keys. It could be RSA, it could be elliptic curve or Diffie-Hellman or any of the other key exchange protocols. But fundamentally, it's using this principle of a split key. The actual encryption of your data itself is going to be done using a symmetric algorithm. So in our case, it was AES, but it could be things like Blowfish or Twofish or any of the other symmetric algorithms. So hopefully what this gives you is it gives you a bit of familiarity in kind of how some of these systems work. I hope. Okay, so we covered quite a lot quite quickly there. So the workshop I've done over the last 2 days, we kind of went through this a lot slower with lots of code examples. Whereas obviously I've tried to jam this into an hour. But we've covered random numbers, so we use those for generating our encryption keys, our IVs, salts for passwords. We've looked at hashing and HMACs, so they give us our integrity and authentication. Enables us to tell whether something's been tampered with. If you've ever downloaded software from some sites before, they sometimes give you a little bit of text underneath which says the MD5 or the SHA-256 hash for that piece of software. That's so that you can check what you downloaded matches what was on the server. We looked at secure password storage. We looked at various different methods of doing that. Plain hashing of passwords, whilst it used to be sufficient, is now easily a problem. It can be easily attacked. Salted hashes of passwords is a much better solution, but with Moore's law and the advent of GPU technologies increasing kind of tenfold every year, you can't guarantee how long those passwords are going to be secure. So we looked at a method for we looked at a method for deliberately slowing down the hashing process, so that even if you're using a powerful GPU, it limits the amount of passwords you can try and crack in one go, which is very useful. We covered symmetric encryption. In our case, we looked at AES. .NET Core has recently given us AES-GCM mode, which is brilliant. Lots of other systems have had it for a long time. It's taken Microsoft a while to catch up, but they've got there. RSA, we looked at as an example of asymmetric cryptography. A mathematical process for generating prime number-based keys. It's a very good transport for swapping keys between two people, or two symmetric keys between two people. And then we looked at digital signatures, which gives us non-repudiation. So being able to prove that it was you that sent a message or a piece of data, which is a very valuable thing to be able to do, to try and get trust. And we then looked at how to combine some of these together, just to give some kind of examples of how things like TLS or end-to-end chat systems work. So when people are talking about end-to-end encryption in the press and about how evil it is and governments want to get rid of it, it's this sort of thing that they're trying to stop. Okay, so what next? Some pretty good books here that I recommend if you're interested in going a bit deeper on the subject. The Code book by Simon Singh is kind of like a history book, reads a bit like a novel. It's really, really good. Starts from like the ancient times of when they used to get soldiers, shave their heads off, write messages on their heads, wait for their hair to grow back and then send them on their way. Brilliant, genius. And it goes right the way through up to kind of reasonably modern digital cryptography standards. So it's just a really fun book to read. Everyday Cryptography by Keith Martin is a much more mathematically dense book that talks about how a lot of the algorithms work internally. So if you're genuinely interested in that sort of thing, that's a good book. But then it talks about how they're used in practical uses. So things like how a cash machine or an ATM negotiates between the bank, how TLS works, how encrypted streams on like Netflix, things like that work. The final book, Applied Cryptography, is the book that they tried to ban in the 90s. It literally was banned at one point. It doesn't cover AES because it came out before AES was around, but if you want a really, really deep mathematical guide on how a lot of the algorithms work, that's the book for you. I've tried to read it and gave up. It beat me. It was too mathematical. If you're on Pluralsight, I've got a few courses here that you might find interesting. So Practical Cryptography in .NET kind of talks about what we've done today, but in more detail. I'm looking to update the course soon, so all of the source code that comes with that book is kind of .NET framework based, but pretty much everything in there will run on .NET Core, it's just a project files with different formats. But I'm hopefully going to try and get that course updated this year. The one behind, Play-by-Play Enterprise Data Encryption with Azure Revealed, is just me talking about Azure Key Vault and how that works. It's a good way of protecting encryption keys online in Azure. And if you're interested in kind of how hashing can be useful as a tool in cryptography, I've got a course called Blockchain Principles and Practices, where we talk about the theory of blockchains, kind of how they are, how they work, what they could be useful for, where they're not useful. And throughout the course, we actually build up an implementation from scratch of a kind of a working blockchain. It kind of just teaches you the principles, which you might find fun. So with that, thank you very much. I think you've got one more talk left to try and stay awake for, so good luck.